discuss a few problems. First giving you the opportunity to give a sketch of the solution and then discussing the solution in full detail, and also giving you some hints where you should concentrate on and what the best way is to solve such problems. Let's first take a quite famous problem. It's called the K selection problem, and that's the following. Suppose that you have a set of numbers collected in an array, A1 to n, and you have to select the kth smallest element of these n elements in an array. So the smallest, of course, is the minimum, but then you can have the one with smallest, etc. Now you have to select the kth smallest element. Now, without going into detail, we know that basically your choice is confined to two algorithms. The first algorithm gives you a solution by a divide and conquer approach, and given a size of m numbers, it reduces it in time O log n and om work to an instance of the same problem. So you concentrate on the data that really are important. That does not affect the original solution, but reduces the set of numbers you have to worry about, and this set of numbers is 3m divided by 4. So 3/4 of the original set are preserved, and the rest you don't care for. So you can reduce that ultimately to a constant number of and then finally you could retrieve the element. There is another algorithm B, and that solves the case selection problem in O log n time and n log n work. And now, by using some technique you should be familiar with, you should find an algorithm that solves the case selection problem by combining these two algorithms and giving you an algorithm that uses less work and slightly more time. So this algorithm gives you in O log n time and O n log n work the final result. We know from theory that this algorithm is not really optimal. It should be the O of n, and you are required to find such an O n work algorithm that computes the result in O log n times log n. Okay. First of all, what is the technique that you are using? So, do you know the name of this technique, and how would you proceed? So, what is the basic setup for this algorithm? It's accelerated cascading, and can you tell me how, well, let's say, the skeleton of the algorithm that's solving it?
I can't.
But you can, of course.
No, I've only read the text. I don't know how the technique works. I know.
No, but well, okay. Give me an intelligent guess then. Just what would you like to do in order to solve this problem, and how would the basic structure of your algorithm in terms of algorithm A and B? So the first question, of course, is, can I start with algorithm B? And then the answer should be no, because algorithm B takes too much work. So what should you do? Yeah.
Use the first algorithm.
Yeah.
To reduce the problem to a size where n log n of that size is going to be able to order it.
Okay. And can you give me also a rough measure of, well, let's say, the size you should use in order to give algorithm B an opportunity to work upon? So what would be an appropriate size for the reduction of the input to be obtained to allow for algorithm B? but what I would like to show you is that these problems can become quite hard if you try to solve them in an exact way. And so if you would like to determine the minimum amount of iterations needed to exactly satisfy the restrictions, then it could become quite hard in such cases. But you should look at this figure taking the required amount of work that you can do in some approximate way. So can you give me a reduction in the input size that would work? For this amount of work. What do you think about, well, reducing the input such that you obtain an input size of n divided by log n? That would work, isn't it? Because then, on an input of n divided by log n, the total work would be less than or equal to 3 over n. So that would, so, well, analyzing and exercising that way can make it life quite easy. And so let's just guess that, well, a reduction to n log divided by log n would work. How would you determine then the number of iterations? So if I perform k iterations, what is the resulting size of the input? Every iteration results in a reduction from m to 3m divided by 4. Well, if I take n as input, then after one iteration I have 3n divided by 4. After 2 iterations I have 3/4 to the power 2 times n. Then 3/4 to the power 3. So after k iterations I have a size 3/4 to the power k times n. And then I have to solve k from the following equation. 3 divided by 4 to the power k times n should be less than or equal to n divided by log n. Yeah. And these are the basic equations. And from that on, you only have to verify that indeed you meet these bounds. So the basic idea is the following. Well, first of all, we should reduce the input to n divided by log n. And well, note sometimes your initial guess can be somewhat unlucky, but well, I always fabricated these exercises that with an intelligent guess with respect to the reduction, you should succeed. So n divided by log n is sufficient. Why? Well, if you take the algorithm B, which costs you n times log n, it now will cost you n, and that's equal to n divided by log n, times the log of that number, n divided by log n, and then you should approximate. So keep in mind that log n divided by log n is less than or equal to log n, because here you divide n by a positive number. So that's less than or equal to, or the order of n divided by log n times log n, and that's the O of n. And well, please take these computations a little bit relaxed. What I see in your solutions is 2 or 3 pages of derivations to convince me that this is less than or equal to the O of n by all kinds of complicated operations, but that's not needed. And you should really take these features of the O operator into mind. The O operator is some kind of approximation. Use it to make life easier. So the O, so the amount of work is really O of n, and if you take the amount of time, well, the O of log n divided by log n, of course, is less than the O of log n. Yeah? So if you take B as well, let's say the closing part, then you satisfy the restrictions. O n O log n. And now we have to make sure that in the first part the same happens. So if we would like to reduce our input size to n divided by log n, well, we solve for the following equation. After k iterations, your input size is reduced to m, where m is 3 divided by 4 to the power k times n, and that should be less than or equal to n divided by log. Well, then there is a simple derivation for solving k, and this derivation ends in k is at least log n divided by the log of some constant. So this is really something in the order of log n. Yeah? Okay, that's the basic idea. And now, once we have found k, we know what the time and what the work cost of our first part of the algorithm, namely the iterations, the number of iterations of k is. So, well, the cost of the resulting algorithm consists of first applying a k times and then b. Well, what's the total time we need? Well, that's the time needed for b, that's this part, plus the time needed for a. We already know what a cost, that's the O of log n. The time needed for a, well, the profile was the log of the input. That determines your cost for reducing. Well, in the first iteration step it is log n, then in the second iteration step it's log 3 divided by 4 times n, and finally it is log 3 divided by 4 to the power k times n. Yeah? Now, again, this might become quite complicated, but why not being somewhat relaxed and using the fact that you know already what the size is of k. K is of the order log n. So, well, of course we know that every of these terms is dominated by log n. This is slightly smaller than log n. This is also slightly smaller than log n. So each of these terms is less than or equal to log n. How many terms are there? Well, log n terms, namely determined by k. Yeah. So here we have a time equal to log n times log n plus log n, and that's of course dominated by log n times log n. Yeah. It could become quite complicated if I had required here a sharper timer, but I don't do these nasty things, so you can really use these all factors. Then what's the total amount of work? Well, the amount of work is determined by the amount of work of A, this part, and the amount of work of B, that's this part, it was the O n. The amount of work is the O of n, the O 3/4 of n, O 3/4 to k of n, and of course we know that the sum of this series converges to a constant times n, and that means the O of n. The O of n plus the O of n equals the O of n, and there you are. So please avoid all these complicated operations if by using some approximation you can obtain the final result like this. Yeah? So, this was a question about accelerated cascading, and well, once you are used to them, they are not that hard. But you should of course be aware that I can slightly vary on the scheme by asking you for a composition of, for example, 3 algorithms to make up a scheme where some of the constraints are found. Okay, an algorithm of a question, a series of questions about a completely other problem. Suppose that you have an array of numbers, and well, the first question is simply find out for me whether or not this array is sorted. And you have to do it in one time. Secondly, could you give me an algorithm that checks whether or not each of the elements in A occurs uniquely in A? And finally, that's the most complicated part, given parallel algorithm to collect all the unique numbers in an array B, and finally tell me how many different elements there are occurring. So you should give me some idea about the uniqueness of elements in there. And for each of these algorithms you have to provide time and work context. Now, A, if you think about it, is really simple. And that again can save you quite some time if you use this idea. So what idea would you use? You have to give a CRCW, of course. Eh? Yeah.
You can start parallel loop workers taking for the sorting between each element and writing to the same variable because you have concurrent read and write. If you find an element that it's not sorted, you just update that variable to true. And then after all the parallel computation is done, you have the answer if it's sorted or not.
Okay, so indeed, I think that your basic structure is correct. So you just assume that the array is sorted, so you set some variable to true. Yeah? And then in a parallel loop you check adjacent elements. Yeah? And once you find a violation of the sorted property, that means that an element is larger than its right neighbor, then your assumption is violated. So you set the variable to false. Yeah? Okay, that's the only thing you have to do in that loop. So the basic algorithm is quite simple. Here, you begin by assuming that your array is sorted. Then for I between 1 and n minus 1, you compare all adjacent elements. If you find one that violates the property, then your array is not sorted, so you return answer false. Yeah? So you set answer to false. And finally, you return the answer. And this, of course, requires a CRCW. Why? Well, you are writing for possibly more violations to the same memory location. So, well, you can easily see that this algorithm costs you constant time and O(n) amount of work. Yeah? And it requires CRCW. Okay. Let's look to the second question. So give a parallel algorithm on a CRCW to check whether each element in A occurs uniquely in A. How would you like to solve it? Yeah.
Again, I'll use a for loop for each element, but now I would update a variable for each element. In case I find the same one, now that variable goes to false.
Yes.
So, and then our last step would be to check all these variables that you have at least one.
Okay, so again, you could use the same idea here. You just assume that every element is unique, isn't it? In the first, so you could assume that every element is unique.
Yeah, the same.
And then you detect violations.
Yes.
Yeah? And once you have found a violation, you return it in the form of a boolean. Yeah? And how would you detect violations?
You, for each element, you instantiate a loop, take this value if you can find it again later on.
So you check for each element present in the array whether it occurs elsewhere. Yeah? Okay. Yeah, that's the case. So here it is. So you start setting the variable answer to true. Yeah? And then for I less than j between 1 and n, you do a par-do loop. If ai equals aj, then set the answer to false. Yeah. Well, that's sufficient, because then finally you return the answer, and then the algorithm gives you the correct result. So the basic message is here: if you have to check, then it's often convenient to just set a boolean indicating that you did not that there did not occur any violation, and then actively check for violations and modify your answer accordingly. So again, this algorithm costs constant time, but now of course O n squared work. Because here you have n squared checks. Okay. Well, how about the final problem? So, give a parallel algorithm to construct an array B1n, such that every element of A is occurring uniquely in B, and B0 is the number of different elements occurring in A. How would you do it? Here the problem is, of course, if there is an element that does not occur uniquely, you have to determine a representative of this unique element. Yeah?
I would use from the B a general instruction for each element that if violates the uniqueness,
Yeah.
and then I would update the B depending on that. Sorted.
Mm-hmm.
You understand what I'm trying to say? For each element that I don't have uniqueness, I just copy it. And then for the next element that if it's unique, if it's not unique, I just copy it once and then try to find the next thing.
Okay, but of course you have to find out whether or not this the second element already appeared earlier in the array. Any ideas about that?
You can, you can, for all elements,
Yeah.
you initialize a array
Yeah.
with all zeros,
Yeah.
for example,
Yeah.
and then you, for each element, you take the element as the index of that array, and then write a 1 to that position. So then you get an array of ones
Yeah.
where elements are not, and then just delete all zeros, and then you can use prefix sum to calculate each zero.
Exactly. So here, your solution is, suppose first take the same idea here, assume every element to be unique. Then check whether doubles occur by taking this loop for I unequal to j between 1 and n. And if so, set Cj is 0 for the larger element. So every time if you occur there is a predecessor that's already in the array, indicate that this is not a unique element. Then if you give a prefix counting of C, you exactly count all the unique elements, because the other elements are all equal to 0. So if you do a prefix counting of C, you get an array D, where the total number of unique elements occurs in Dn. It's a total number of ones that appear in C. The total number of ones, of course, you can put into this B0. And if di equals k, it means that I is the kth unique number. Yeah? If ci then equals 1, you know that ai is the kth unique number in A, so the bk equals ai. Yeah? So here's the algorithm. For 1 to n Pardu, initialize ci to 1. That's the assumption. Then for j larger than I between 1 and n, Pardu the following. If ai equals aj, then it is a violation of the uniqueness, so set cj to 0. Yeah. Then perform a prefix sum to this array C for n elements and store the result in D. Set B0 to Dn, that's the total number of unique elements, and for I between 1 and n, search for the ith, for the unique numbers. So if ci equals 1, then bdi should equal the a of I. And there you have, of course, your array of unique numbers. What's the cost of this algorithm? Well, of course, it's dominated by the prefix sum computation, and you know that in this for loop we have an O n squared amount of work. So time is log n and work is yeah? Okay. So please be aware that in all these cases I use the technique of, well, if you have to check for a property, or if you have to do some computation, to perform some computations using a property, it's often quite useful to start with the assumption that the property holds for some elements and then just count the violations. Okay. Next. So given an array of positive integers, present a w n log n, and t is log square n parallel algorithm to obtain an array b in numbers such that every element of A is either occurring uniquely in B, or every element in B is either 0 or occurs in A. And every element in B is either 0 or occurs in A. So basically what this tells you is that B should contain the unique elements in A, and else should contain zeros. Yeah? That is a possible solution. Yes?
Use the same technique as in the previous exercise, but now when you go to B, instead use a balanced tree method and copy all the values, but when you say false in the uniqueness,
yeah,
copy, place a 0 in B.
Yeah. Okay. Yeah. That's indeed this scheme. That is a possible scheme. And of course, there are two ways of solving such a problem. That is, if you have a consecutive set of exercises, it's very tempting to use the same technique that you already applied in the previous exercises, and usually that leads to a good answer. But sometimes it's also necessary to try to find a variation on that scheme and to use another technique to make it more easy. And here it is very easy, and well, that's of course also the hint that's given here by mentioning the work and time complexity, to use another technique, a pre-processing technique that makes it more easy to find the answer. Hey, so here if you see an n log n, that should remind you already of sorting. Yeah. And the O log square n, of course, too. Yeah. That's because of this fast parallel merge algorithm. So the idea now is start to sort A, and then you can easy find the doubles by checking adjacent elements. Yeah? Because if adjacent elements are equal, then the second of these adjacent elements should receive a 0, and else it should receive a 1. So if AI minus 1 and AI are equal, AI is not unique. If AI minus 1 is less than AI, we set BI equal to AI, and we know AI occurs uniquely. Yeah. Else we set BI equal to 0. Okay. Here's the solution. So first we perform a parallel merge sort. We set A0 to minus 1, and then for I between 1 and minus 1, we compare I minus 1 with respect to AI, and we set BI to AI. Note that here, of course, we have to add to the array an element minus 1. Yeah. And that's because of AI contains positive integers. So it should be distinguished because A1 always should occur. So BI should be set equal to AI, and else BI should be equal to 0. Now, the costs are clearly dominated by this parallel merge sort, and that means that T is log square and W is log n. Of course, there are several ways of doing this, but this is a particular variation that will cost you less time. And well, be aware that in general, during the examination, I will try to make clear what is allowed for you to do without mentioning the underlying algorithms. So for example, in the previous algorithm I used prefix sum without giving you the full detail of the prefix sum. And so in some of these exercises I will allow this to use simply an abbreviation, parallel merge sort, prefix sum. In the other exercises it could be that I require every algorithm to be explained in full detail. Yeah? That will be made clear from the context. Okay. A completely different one. So assume that you have given a linear recurrence, and you have to consider the matrix Y of solutions. You have to compute an efficient parallel algorithm for Y. And then secondly, I would like to make a slight change here to this recurrence. So instead of here taking a very simple recurrence, I would like to take here a y minus 1 y minus 2, and I would like to study the consequences for the algorithm. Yeah. So first of all, concentrating on this first linear recurrence. You already see that it is not in standard form. How would you bring it in standard form? So what's the standard form of such a linear recurrence? That's yi is some matrix times yi minus 1 plus some factor b if necessary. How could you bring this second equation into that standard form? in this case it's not that difficult. Here, what you do is simply rewrite this A to a new matrix A plus the identity matrix. Yeah? And then you see that the yi equals the A plus the identity matrix yi minus 1. Yeah? And now, again, this constant vector you don't need. So this constant vector is 0. Well, the particular name for the resulting system of equations, where you have one matrix that is used as a pre-multiplication to obtain the next vector in your system of equalities, and the original vector b equals the 0 vector, except for the initial ones, then we have a Krylov system. And for this Krylov system, we know, or you should know, that we need the O of log n times log n. So it is log m for the matrix multiplication, and it is of course log n because we have n of these entries, log n time, and the O of n to the power 3 times log n operations. Yeah? So this is a very simple one. The only thing you should be aware of is forming this new matrix. Yeah? The second one is somewhat more involved and requires that simply trick to condense your, or to extend your original set of equations, now not to vectors AI, but systems of vectors of combinations of yi terms. So, for example, I had the original equation yi equals ai minus 1 plus yi minus 2. Yeah? Okay. Now I take a combination of yi and yi minus 1, and here I fill in the original form, and here I just repeat. So here I make a dummy equation. So this is the second term. And now, if I expand this, I get the following matrix: A identity matrix 0, yi minus 1, yi minus 2. Yeah. And this, of course, can be formed as a new system of linear recurrences if I take zi as the combination of the former vectors yi and z1 equal to b. Now, then I have the same system of equalities basically as the previous one, but now not with n, but with 2n, the length of a factor of length 2. Yeah. And this is again a Krylov-like system, and it will cost you the O of log n times log n, and the O of n to the power 3 times log n operations to complete. Yeah. It does not matter whether or not I blow up my vectors with a constant number. It does not give you a different time the complexity profile. So, okay, and then of course finally I should be I should spend one time to retrieve the original solutions yi from these equations z. Okay. Well, okay, that's sorry. I had to offer you here the question first. But okay, let's deal with this last exercise. I have a few slides more you can study on your own. We did discuss the rank operation, and the rank operation was the following. If I have an element x and I would like to determine its rank in an array A, then the rank of it is the number of elements that are less than or equal to that given element that occur in A. And now I would like to deal with the fact that A is sorted. And I would like to find out a parallel algorithm on a CREW, so not a CRCW, that computes the rank in one time and O in loop. And so supervised the fast rank determination. Yeah. And of course, if you know that A is sorted, it would be tempted to use a binary search, but that would not provide you any speed up with respect to a sequential algorithm, because we can do it in log n. Yeah? Yes? You are-
The elements are unique.
Yeah.
Oh, so
Yeah,
okay,
yeah, yeah, yeah. Yeah, sorry. Yeah. Yeah. That's a good question. Yeah. I had to add it. Yeah. So, let's start. So, first of all, we have to check whether the computation could be trivial. In the sense that x could be less than a1, or x could be at least as large as the a of it. Because in that case, well, we can immediately provide the answer, 0 or a. If that's not the case, then we know that a1 is less than or equal to an. Okay. We know that since a is sorted, there exists a unique j that's larger than 1, such that aj is less than x and aj minus 1 is less than or equal to x. So in this case, I already sorted it may be, sorry, I could provide you with the hint that they should be unique, but in fact here that is not needed, because you take the first in the sorted. So there is a unique j with this property, isn't it? Okay. How to determine this j? Well, use the property itself. So look, in parallel, for the occurrence of such an index j. Now you should be aware that this uniqueness property is very important for performing it on a CREW. Because if the index is not unique for which this property holds, then you can't use the CREW property, and you should use the CRCW property. So there is only one index for which this property holds, and that index determines, of course, the rank. Yeah. So, if ai minus 1 is less than or equal to x, and ai is larger than x, then we return I minus 1 as the result. Yeah. Okay. Here's the algorithm. If x less than a1, return 0, larger or equal to an, return n. In all other cases, find this simple unique index I and return I. And here, of course, it's very crucial that I know that there is exactly such a unique I, because otherwise we could have a violation. Yes?
Now we have exclusive, right? But if the index isn't unique, then you wouldn't write to the same location, right?
No, but there are, in certain sense you do, because if you have an output variable that whose contents will appear as the result of your algorithm, you could have an indeterminate result.
But you write to an array, but you write in different places, right?
Okay, but suppose that that your output channel is used to retrieve your answer. It's kind of memory location, isn't it? You are writing to your output channel. Yeah. Okay. And therefore, it's very important that you realize that this violation, and that also should appear in your solution. There should be an argument why you could use the CR. Yeah? Okay, are there any other questions? Okay. I have a number of exercises that you could study further. They are all provided with solutions. There is a test exam also you can consult via Blackboard, and if there are any questions, then please feel free to ask them. Yeah. Of course, I can't answer all questions directly. You could come up with a question that I would like to include in the examination, but else then I will be able to answer. Yeah? Okay, then there were some students here asking me for explaining something about mathematical reduction. Yeah? Okay, please come forward. So for the rest, it's over now. I wish you all the luck.